Okay, section 5.2, sigma notation and limits of finite sums. This is going to help us build on what we did in the last section, and I still have those notes here from the last section. We added up rectangles, added up areas of rectangles. And we could sort of see this was getting cumbersome. This is only 4 rectangles here, but that was kind of cumbersome. Imagine if I had told you to do this with 8 rectangles. Just writing that out 8 times is a little bit cumbersome. So in this section, we're going to get some better notation to help us deal with this repeated addition, and so that the notation at least isn't as cumbersome. And so what we're going to get here to help us with that, go in a little bit, is something called sigma notation. The following is sigma notation. Sigma notation is used to indicate sums. So very generally, and this would be read, the summation from k equal 1 to n of a sub k is a1 plus a2 plus a3, all the way up to whatever n happens to be. And what that a generally is going to be is some sort of formula, where you're going to take that formula, you're going to plug in 1, then 2, then 3, and however far you need to go up. The Greek letter sigma is the summation symbol, and it just indicates repeated addition. The k is called the index. Other common letters used for the index are I and j. The 1 at the bottom and the n at the top are the limits of the summation. Limits, note, summations may start at any whole number. And so they can start at 0 and then they go up by 1. So you can start at 0, 1, whatever your problem happens to need can become the beginning of a summation. Generally, summations, depending on what the application is, it's probably usually either going to start at 0 or 1, but they can start at anything. And then n is the upper limit, and that might be a number. Sometimes, as we see in the future, it can even be infinity. It just depends on the problem. Write the following without sigma notation, then evaluate the sum. And so the point here is just to get used to sigma notation. So the first thing we're going to do is we're going to start at 1. And so for k equal 1, we are going to get 3 times 1 plus 1 over 1 squared. Then we go up to k equal 2. And we'll get 3 times 2 plus 1 over 2 squared. Then we're going to go to k equal 3, which is 3 times 3 plus 1 over 3 squared. And then k equal 4, 3 times 4 plus 1 over 4 squared. And then just do the evaluation, and the arithmetic really isn't the point here. What that's going to give me 4 on the first one. This next one would be 7/4. The third one would be 10/9, then 13/16, and then whatever that equals after that, you would need a common denominator. Yeah, and I just have no clue what that common denominator is right off the top of my head, so I'm not going to bother. The point is not the arithmetic. So if there's a homework problem here on the computer and they ask you to do the arithmetic, just take out your calculator and do the arithmetic. The point is not the arithmetic. So whatever that equals, point not the arithmetic. The point here is understanding what summation notation means. So the point not the arithmetic. Feel free to do that on a calculator if you want. But I just honestly don't want to get, no, the common denominator would be at whatever 16 times 9 is, and yeah, I just don't want to do that. Okay, doing this next guy. So this is going to equal, we'll drop down here so we have enough room. For k equal 1, we're going to have negative 1 to the 1 plus 1 cosine of 1 pi plus k equal 2. And this would be negative 1 to the 2 plus 1 cosine of 2 pi. And then k equal 3. Negative 1 to the 3 plus 1 cosine of 3 pi. So, showing every detail here, and I can zoom out just a little bit. Showing every detail here, what that's going to be negative 1 squared cosine of pi plus negative 1 cubed cosine 2 pi. And I'm showing every step I can show here. Negative 1 to the 4th cosine 3 pi. And so that's going to be cosine pi minus cosine 2 pi plus cosine 3 pi. That just taking care of the negative 1 to each exponent. Negative 1 squared is positive, so positive 1. Negative 1 cubed, negative. Negative 1 to the 4th, positive. And the reason why I just explicitly wanted to say this is something you're going to see for those of you that end up in Calculus 2. This negative 1 to the k plus 1, and sometimes you might see negative 1 to the k, or negative 1 to the 2n plus 1. It just kind of depends. But what that negative 1 does is it causes my signs, SIGN, to alternate. In this case, positive, negative, positive. And if it went further, we would keep seeing that alternation of signs. And so we're seeing this alternating. And that's just something you're going to see later on in Calculus 2. And that's just that effect of that negative 1 causes the signs to alternate. Now finishing out the arithmetic, cosine of pi is negative 1. Cosine of 2 pi is 1. Cosine of 3 pi is negative 1. And so this whole answer is negative 3 pi. So there's going that way, just understanding what summation notation means. Then creating summation notation. So, express the following in sigma notation. Use 1 as the lower limit of the summation, k for the index of the summation. And so what they're wanting you to do is find the formula and then do the summation. Now, I will be brutally honest. I really hate these sort of problems. And so don't expect from me anything more complicated than what you see here. I really hate those sort of problems, those little brain teasers you sometimes see where there'll be a list of numbers and they'll say, what is the next number? I can never do those if they get any more complicated than these. So if you hate these problems, you're lucky. I hate them too. Again, we're just going for what the concept of summation notation is. And then later on, when you get to chapter 10, sometimes you're going to have to identify some patterns and then find some formulas, but they won't get much more complicated than what we're seeing here. So let's just notice on this first guy that this really is 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And that very clearly gives me kind of what the formula should be. That we're going 1 to 5, and then each time we're just squaring. So I could say that this is going to be the summation from k equal 1 to 5, because they said start at 1, this goes to 5, and then what are we doing each time? We are just squaring. And so there would be the notation, the summation for it. And then you can think about it. If I start at 1, square it 1 squared, go up to 2, square it 2 squared, go up to 3, square it 3 squared. And so there's my summation. Okay, the next one. Let's note that it alternates. And so we said something about that before, that alternation, so the formula will include either, for our purposes right now, negative 1 to the k or negative 1 to the k plus 1. It's going to be one of those two at this level. It can be mathematically other things, but for our purposes, it's going to be one of those two things. We need to start negative. We must start with k equal 1. Because they told us that. K equal 1. And first term, start with k equal 1, with first term positive. Oops, no, first term negative, just looked at it. First term is negative. Should read my own problems. So you look between these two things. We want the first term to be negative, starting with 1. Well, if I happen to think about negative 1k plus 1, if I put a 1 in there, that'd be negative 1 to the 1 plus 1, negative 1 squared, which is positive 1. So I need to choose this guy. And so we will choose negative 1 to the k. Because if I put in negative 1 there, if I put in 1, that's going to be negative 1 to the first, which is negative. So I'm going to go with negative 1 to the k. So my summation is going to be k equal 1 to 6, because it goes up to 6. Then we decided that there'll be a negative 1 to the k, and now getting the rest of the formula. Well, each and every time, the denominator is just 5, so that's easy enough to get. And the numerator just goes 1, 2, 3, 4, 5, 6. Well, that's just what's happening to k as k counts up. So my numerator is just going to be k. And there's what will do it for us. So again, don't worry too much if you can't do these things when the patterns get really, really out there. You're not going to have really, really out there patterns. The point here is just understanding the relation, understanding what summation does for us. Okay, there are a few summation rules that we will be using. First rule, the sum rule. The summation from k equal 1 to n of a sub k plus b sub k equals the summation from k equal 1 to n of a sub k plus the summation of k equal 1 to n of b sub k. In words, summations can be broken up by addition. Similarly, the difference rule, k equal 1 to n of the quantity a sub k minus b sub k equals the summation from k equal 1 to n of a sub k minus the summation from k equal 1 to n of b sub k. In words, summations may be broken up by subtraction. 3, the constant multiple rule. The summation from k equal 1 to n of c sub c times a sub k equals c times the summation from k equal 1 to n of a sub k, where c is just some sort of multiplied constant, 12, 14, 92. It's just a coefficient, basically, multiplied coefficient. Yeah, it doesn't even, just multiplied coefficient. I said constant. We're going to do some things later where it gets a little fuzzy, but we'll talk about that later. In words, a constant multiple can be factored out. So there are our first 3 properties. More properties. The constant value rule. So this gives us one of our first kind of formulas. The summation from k equal 1 to n of c is c times n. And that makes perfect sense that, say you were adding up 2, from adding up 2 plus 2 plus 2 plus 2. You can just take the number of 2's and multiply by it. So that makes perfect sense. But there's our first little formula. K equal 1 to n of c, where c is just some sort of number, is c times n, where n is that upper limit there. In other words, the summation of a constant is equal to the constant times the summation. And we will stop this video and do this first problem on the next video.